Um, these problems, a couple of them have subsections. Okay, so these are the kinds of problems you can expect. So you will have one or two problems on the Poisson distribution. Now the Poisson distribution problem, either I tell you that something's Poisson distributed, or it looks like it's binomially distributed. Now, binomial distribution you can always see when a random variable has binomial distribution, because if it's in a setting where your random variable x is counting the number of successes, where you can call something a success. So if x counts the number of successes, then that is binomially distributed. So somebody had a question of when do you use the Poisson approximation, when do you use the normal approximation. Remember, the Poisson approximation was n going to infinity, but p going to 0. So that's when n was large, but p was small. So the condition you check, if you want to use a Poisson approximation, if p is getting small, that means np is not going to get too large. Right? So basically, if you're going to use a Poisson approximation to a binomial, either I'd say use a Poisson approximation, in which case you just use the Poisson approximation. Otherwise, if you want to, you need to check this condition. N has to be large, and for p to be small, you just check the value of n times p. N is large, but that means p is small enough that np isn't blowing up. So np is less than or equal to 5. If n is not so large, if n is small, but for smaller n, if n times p is in the range of 1 or smaller than that, then you use the Poisson approximation. Some people want to know when to use the normal approximation to binomial. Here n is getting large, but p is not getting small. Okay? So if p is not getting small, then n times p is also getting large. Okay? So basically you check the condition, and I think in the write-up I said it's best to just check that this is greater than or equal to 10. So if this is greater than or equal to 5, also you can use the normal approximation, but greater than or equal to 10 is best. So here for the Poisson approximation, p was getting small, so you wanted n to be large, but n to be less than or equal to 5. Here n times p times a fraction which should make it smaller should be larger than 10. Okay. So this is the condition you check if you want to use normal approximation to binomial. So if you have a problem with a binomial random variable, and you're asked to calculate some probabilities of these binomial random variables, either you can use the binomial distribution, or you can use a Poisson approximation if this condition holds, or you can use the normal approximation if this condition holds. Both of these cannot hold, because if np is less than or equal to 5, if I multiply it with 1 minus p, it gets a bit smaller. Okay. So if this holds, use Poisson. If this holds, use normal. All right. So that's when you have binomial and Poisson. So you have a couple of Poisson distribution problems, a couple of binomial distribution problems. So Poisson distribution problems. So binomial distribution, you will definitely see problems based on binomial distribution. So basically you will have to guess that it's binomial, and then you have to identify your n and p. If it's Poisson, you need to identify your parameter lambda. And the way lambda can be given to you is, I could give you the average value of your random variable, and that would be a lambda. So that's how you get information about lambda. Information about n and p is, if you interpret the question right, you get n and p automatically. Now, p is probability of success at each trial, n is number of trials, and x counts the number of successes in these n trials. So any problem where you have n Bernoulli trials, probability of success at each trial is P, and if X is number of successes in these n trials, so it counts the number of successes in your n trials, then X will be binomial distributed. So cosine binomial, you may have a problem on geometric distribution. Then under uniform, under continuous distributions, you will have problems on all the three. Uniform, exponential, and normal. Now, okay, so I'm going to tell you something more about the normal distribution. Again, with all these, you can have them sort of like compound problems. So even though you're not going to be tested on conditional probability as such, you might have problems where you're using conditional probability. So you'll have a few problems in your homework where you use conditional probability. So you need to remember your conditional probability formula. So probability of any event A condition on B is probability of A and B divided by probability of B. So this is a definition that you need to remember for your conditional probability problem. So, and of course, for exponential distributions, you have a nice property for exponential. That is, if I look at probability of X conditioned, if I say X, if I condition on the fact that you know X is greater than T, what's the probability that it is greater than S plus T, that is an additional amount S? This conditional probability is just, this is called the memoryless property. Which makes calculations very easy for conditional probabilities in the exponential case. This is, the memoryless property only holds for exponential, not for uniform, not for normal. There. So one of the problems where you had conditional probability mixed in with these continuous distributions, I think that was on page 225, problem number 21. And then you had some problems where you had a combination of these distributions. The continuous distribution as well as discrete. So you had a problem where you first had to calculate some probability using the uniform distribution and then use that in another problem that involved one of these discrete distributions. So these kind of combination problems you had on the homework, I think these were problem number 4, page 224, and problem number, page 225, problem number 16. So you had, so these were problems where combination of two distributions. And lastly, about normal distribution. So some of you are a little confused about when to just use the normal distribution, when to... So not every normal distribution problem is a normal approximation to binomial. If I give you a problem and I say your X is normally distributed, it's a very straightforward problem. You know it has a normal distribution. If I give you a problem, I don't say it's normally distributed, but you look at it, it looks like it's binomial, but this condition is satisfied, you can use a normal approximation to the binomial. In which case you would do a continuity correction and you would have to find NP, you have to find NP 1 minus P to find your mu and sigma squared. Okay. So just to distinguish between these two kinds of problems, turn to page 225. Problem number
This is what we need to study.
I'm sorry?
This is what we need to study.
Yes, so you can expect problems on these topics. Poisson distribution, binomial distribution, uniform, exponential, and normal. And you have to remember conditional probability because you can have some problems where you need to use conditional probability and these distributions and some combination problems. So here are some examples of these kinds of problems. Okay, so these two problems, this one on page 225 and the problem I'm assigning. So I want you to distinguish between, realize the difference between these two problems. Alright, let's start with this problem that I've written down. And for every problem, I'd like you to follow this procedure. Step 1, define your random variable of interest, random variable of interest. Step 2, identify the distribution, probability distribution. Of the random variable, identify the question. Probability. Have you been asked to find it? Okay, so let's follow this method. So for this problem, step 1, define your random variable. Clearly our random variable of interest here is x, the number of the lifetime in hours of the light bulb I bought, right? And this is the light bulb I bought from that company. And everything is in hours, so be careful to put in relevant information. So if it's in hours, make sure you mention hours in your definition. The next step, identify the distribution, and here's where you have a really simple problem. I've told you it's normally distributed, so right away, I have this. The mean mu, what is mu? I've given you mu is 900, and sigma square is, so I've given you standard deviation, that's sigma, so this is 150. I always write it in this format, 900, 150 square. So once you've done that, the next thing is, what do they ask us to find? What is the probability that the lifetime is greater than or equal to 980? Okay, the big difference between this problem and this problem, so we'll get to this other problem, is that in this problem, you're given that X is normally distributed.
Will you be providing normal tables?
Yeah, yeah, I'll provide you the normal table. So don't worry about that. I'll provide you the normal table. So yeah, so I'll have a sheet like this at the end of the exam. Okay.
I shouldn't have memorized all those.
Yeah, if you want to memorize those, go ahead. But I'm telling you, you don't have to.
Took me all spring break.
That's what he did over spring break. What fun. Okay, so X greater than or equal to 980. Okay. So before we get down to that, let's compare it with what we do in problem 220 in problem 20 on page 225. What is the difference between these two? In this problem, okay, so page 225, problem number 20, says if 65% of the population of a large community is in favor of proposed rise in school taxes, approximately the probability that has someone contribute will contain these 15. Okay, so first of all, what is your random variable of interest?
Number of people in favor.
Exactly. So the first thing you write down in this problem, so 5, number 20, X is number of people in favor, blah, 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 tax, whatever. Okay. What distribution is this? Exactly, this is clearly binomial. Your probability of success was given to be 0.65, and you're testing how many people? Sample 100? 100. It was 0.65. Yeah, just about. Okay, so when you look at this problem, you recognize that it's binomial. Now, first of all, they say give an approximate probability of everything that you have to calculate. So if you have to just find an approximate probability, that means you can use an approximation to this distribution. What approximation would we use here?
What number problem is this?
Page 225, number 20.
This one's 22?
No, this is just a problem that I've written down. Sorry. All right, yeah, question.
So if I wanted to let X be the number of people that are not in favor of the proposal, I could do that too by normally distribute it with, and that would just be 45.45.
Exactly.
3.5.
Yeah.
Okay.
Yeah.
Okay.
Yeah. So in both cases, you get NP times 1 minus P. There your P will be 1 minus P and 1 minus P. So you end up with this being 5 times 0.35. What do you get it to be?
22.75.
I'm sorry?
22.75.
22.75. Okay, so this is greater than 10. Okay. So you're going to use a normal approximation. Use normal approximation. So let's calculate the mean. That's n times p. That's 100 times 0.65. So that is 65. And variance, sigma squared is np, 1 minus p, and we said it was 22.75. All right. So now, here, what's the first question asking us to calculate? Let the x at least 50 to unfit by the proposition. probability that x is greater than or equal to 50, right? Alright, so probability x greater than or equal to 50. Now here x is a binomial distribution, right? So if this is a binomial distribution and we know we're going to use a normal approximation, you've got to do this, the continuity correction. Because this is discrete, you're going to approximate it by a normal distribution. So the first thing to do is, right, it says you want to include 50, so go down by 0.5. All right, so this is your continuity correction. At this point, if you say greater than or equal to 50 or greater than or equal to 49.5, it's the same because x only takes integer values. All right, next, I'm going to say x minus mean, which is 65, over standard deviation, 22.75, is greater than or equal to 49.5 minus 22.75 over square root of 22.65. 2.75. Now at this point, I change it to approximation and say that this normalized thing is now, I'm going to replace it with standard normal, now this has become an approximation. Up to here, my x was still binomially distributed. Now I'm approximating it with normal distribution. Tell me what this is. P of z greater than or equal to
The negative 3.14.
negative 3.14.
14.
Okay. So this is 1 minus probability of z less than or equal to 3.1. Negative. I have negative 3.14. But this is if you want, you don't have 5 negative things, so
Yeah,
we're going to write it as 1 minus 5. 1, 4. So different number. So you get 5.
Actually, I'm not sure that's right because I didn't use 49.5. If it's
49.
discrete, do you have to use 49.5?
Yeah, can you see that again, sorry?
If it's discrete like this,
Yeah.
do you have to use 49.5?
You have to do the continuity correction.
Oh, okay.
You're starting off with discrete.
Mm-hmm.
Now when you have z, this is continuous random variable.
Alright.
So whenever you do a normal approximation, let's say this problem is a normal approximation problem. Okay? And now we're going to continue with this other problem that we've done, which is a straightforward normal distribution problem, and you see the difference in our computation. Here, since we started off with binomial, we're using normal approximation, start with continuity correction, change that by 0.5, and that 1 minus probability less than that. That's 1 minus, yeah, okay. I think 3.14 is,
It's actually negative 3.25 because I didn't cut negative.
this,
Yeah.
negative 3.25.
Mm-hmm.
And you can read off what 3.25 is. Give it that. .9994. Alright, so I'm going to stop here with this problem, and we'll come back to this word problem that I've written down here.
Are we gonna do any more parts of that, number 20?
No, I don't think this is.
I just got a little bit confused with one of the later parts, like which way to move that continuity correction, up or down and
Oh,
stuff.
okay, that, we'll do that too, but let's come back to this problem first and then I'll finish up that. So, yeah.
Why don't we use the binomial distribution for this case?
So you can use the binomial distribution, it's just that you're going to have like 100 choose this thing, and you're going to check the probability that's greater than 50, you're going to be summing many terms. You can use it, right? But first of all, the question says find an approximate probability, which makes this calculation easier. If you were going to use binomial directly, x goes from 50 to 100. So to calculate that, you're going to sum up 50 terms.
Yeah.
So you can technically do it, but the error that you get by using this approximation is so small, you probably get more of an error just by rounding up stuff here.
Okay.
So technically you can do that, but it's just this approximation is easy to calculate. You end up with a numerical answer right at the end, which is going to be so close to the actual value that you might as well just use the approximation. Yeah, but let me just write down what. So this would have been choose x. So that's what you would have to sum up for x going from 50 to 100. Technically speaking, that's what you can sum. Okay. All right, we'll come back to this problem later. I want to highlight the difference between these two problems now. So going back to the original problem, the simple normal distribution problem that I started off with. So here, there's nothing like a normal approximation to binomial. There's no approximating going on here. Okay, you're starting off with a normal distribution and you're just using the normal distribution. That's it. So you're given this. Note in this problem, nowhere do I say that x is actually distributed as normal. I have x is distributed as binomial. And I use normal approximation. Alright, so here x is normally distributed, so when I calculate the probability x greater than or equal to 980, it's going to equal the probability of x minus the mean over standard deviation, 980 minus 900 over standard deviation, 50. And here it is not approximate but equal to, this is the property of normal distributions. When I normalize a normal distribution, I get standard normal. And here it's equal, not approximate. Here I have to use approximate. 80 over 150, 8 over 15. So this is 1 minus probability c less than 8 over 15. That's 1 minus 5, 8 over 15. Tell me what that is. So some things that are different here. Here, I'm given that it's distributed normally. Here I'm given that it's distributed binomially. And so I'm going to use a normal approximation. Here there's no approximating going on. When I use a normal approximation to binomial, you have to do the continuity correction. So note the difference between this and this. All right. Next, after I normalize this, when I replace it with the probability of the standard normal being greater than or equal to this, is now approximately this. While here, when I normalize, this is exactly the normal distribution. It is distributed normal distribution. That is approximately normal, standard normal. So these are the places where it's different. Given it's normally distributed, I am not given that. I'm given that it's binomial. When I write this down, I don't use any continuity correction. Here I use a continuity correction. And at this point, when I go from x minus mu over sigma to z is equal, well, here's only approximate. Because here's where here was still my binomial random variable x. Here it is normal. while here it's normal throughout. Okay. Alright, so coming to the different parts for this problem. So you said you had a problem with how to do the continuity correction? Was that your problem?
Oh, yeah, I moved to 0.5 the wrong way. I don't remember
Okay,
how
so
that.
basically you want to make sure you definitely include the point that's out here.
Yeah,
So if I want to include 50, if I go up by 0.5, I've excluded it.
right.
Okay? So the whole point of the continuity correction is because probability x equals 50 is 0 if x was continuous distribution, but it's not if x is discrete, right? So you want to make sure it's included, so you lower this a little bit so that you definitely include 50.
Right.
If you went up to 50.5, you're excluding 50.
Right.
Okay, so you definitely go down.
I think it wasn't this part though. This one was pretty straightforward, but
Okay,
the
so
next,
let's talk about
the one
the
that was
next
like
one.
between this and that.
Okay, let's see.
You still have that homework, right? Or did we
Oh.
get back?
Was this one of the homework problems? I don't remember that. Okay,
I remember
let's see.
doing this one. Maybe
I
not.
don't think this was a homework.
What?
Okay, anyway, this problem, part B.
I did it.
Okay, so we're looking at this problem, part B. Part B, between 60 and 70, and it says inclusive warranty. So inclusive, so it's equal. So first write down your probability in terms of x itself. Now,
Yeah, we did this one.
okay, so if you want to include 60, you definitely want to include it. So you should go down.
59.5,
right?
okay.
Exactly. So if you start with 59.5, you're still including 60 in this. And you want to include 70, so
17.5.
exactly.
Oh, I guess my problem was that I rewrote z less than or equal to 70 as, or x I should say, or whatever, as 1 minus the probability that z is
So this is not yet z, this is still x.
x, sorry, different letter.
So when you're doing the continuity correction, it's still at x. So that's why at this point it doesn't change, because if x is discrete, going down by 0.5 doesn't change it, because it's still only counting x between 60, 61, up to 70. Let's see, fewer than 75. Here, you don't have to do a continuity correction. You can just leave it out. Because if I had included 75, then to make sure that 75 was included, I would have gone up by 0.5. Okay. But since 75 is not included, it's okay. I don't need to include it. So,
If we did it, would it make it incorrect or no?
if you went up, it would make it incorrect.
If you went to 75.5,
It would be incorrect.
it would be,
Yeah.
okay.
Because now you're including 75. Okay, so
Oh, I see, okay.
and you don't want to include that. If you went down by 0.5, it really wouldn't change it so much.
Okay.
So if you went down at this point, it'd be okay. So here, continuity correction, definitely don't go up. You can go down if you like. So you can do this. No, but this still doesn't change this, because x is counting everything up to 74. If I
Okay.
went to 74.5, it still only counts up to 74. So I haven't changed anything. So if you want to do a continuity correction, you would do it, but just make sure that you don't count 75, since 75 in the original problem is not counted. All right. You have homework that's due on Wednesday, right?
Yeah.
What?
Yes.
Oh my gosh.
So how about, okay, I won't collect homework, let's just go over the problems today. Yeah, all right, so I'm not collecting homework this week, you have the exam.
Okay.
All right, so I'd like people to come up to the board and start answering these problems. If you want, you can work on them for a while in groups, but I'd like volunteers to come up and do them in the day.
And this is stuff that won't be on the test?
It is on the test.
It
It
is
is
on
on
the
the
test. Yeah,
test.
you're being tested on normal distribution.
Oh, okay.
The latest homework was a normal distribution, right?
Normal exponential.
Exponential.
Yeah, normal and exponential, right, yeah. Question?
Is there gonna be a problem like 39 on the test?
Yeah.
Yeah, okay, that was the one thing I forgot to get to, right? Yes, definitely, yes. That's the last problem. So you have one problem of that type. It's like this normal distribution stuff. Good thing you asked me. So the last problem is going to be on find the probability density function for a function of a random variable. So you'll be given the density function of a random variable, and then you'll be asked to find the density function of some function of that. So say you're given the density function of x, and you're asked to find the density function of some function of x. See, so what do we do on this problem? So for example, page 227. So problem of that type. All right, so okay, so what were your homework problems? 25 was the homework problem, is that right? Okay, so who do problem 25? 25. 32. Anyone will go into the 32? Okay, how about 33? And then there was 37.
What the hell?
Okay, let's start. 37? Okay, all right. 37 and 39. Okay, so let's, okay, so 25, there's someone willing to do that. Let's look at problem 32. That's quite a bit of space. Okay, so problem 32. What page is that? Page 26. Step 1, define your random variable. So x is the paired time, and it's important to note that everything is measured in terms of hours. Okay, paired time in hours. Step 2, identify the distribution, and you've been given that it's exponentially distributed with rate lambda equals 1 half. Next thing is figure out what the question is asking you to find.
32?
I'm sorry, say that again.
32, what now?
this is problem 32, page 226. The time and hours required to repair a machine. So, okay, so you've been given this exponentially distributed and you've been given the parameters, so very straightforward so far. Part A, find the probability that repair time exceeds 2 hours. Probability x is greater than 2. And remember, since x measured stuff in hours is greater than 2. Supposing x measured stuff in minutes, then you have to change 2 hours in terms of minutes. Okay? So it's important to note that if your x is in hours, you can frame your question like this. If your x is in minutes, then it will be 2 times 60. So it will be 120. Okay, so important to note these little details. Probability x greater than 2, you're given the exponential distribution. You can use calculus and integrate out the density function. So technically, this is what you would do. E to the negative lambda, so 1/2 lambda x dx. Or, what else do you know? That this is 1 minus probability x less than or equal to 2. If you memorize the distribution function, then you might as well just use that, because you don't have to do any calculus then. It's 1 minus f of 2, and that's 1 minus, what is the distribution function? 1 minus e to the negative lambda x, 1/2 x. Very easy problem. This one. So what I've used here is if x is exponentially distributed with raised lambda, instead of using the density function, I use the distribution function. The distribution function is e to the negative lambda x. So probability x greater than 2. This is just probability x. The relation between distribution function and probability is probability x less than or equal to this value. I'm sorry, say it. Okay, so if you don't want to do calculus, remember you can memorize the distribution function, and then it's easy to calculate probabilities using the distribution function, because this distribution function is nothing but the probability that the random variable is less than or equal to this value for the x. Okay, part B. The conditional probability that a repair time that a repair takes at least 10 hours given that its duration exceeds 9 hours. So this is a conditional probability problem. So first thing, frame the question mathematically speaking. What probability have we been asked to find? So basically, you've been asked to find the probability that x is greater than 10, given that you know that the repair time has exceeded 9 hours. Well, here, you know that x is exponentially distributed, so by the memoryless property of, here we're going to use the memoryless property of exponential. You really don't have to do any calculations as such because of this memoryless property. So that it's basically the question is, what's the probability that after 9 hours you wait an additional 1 hour, and that is just the probability that x is an additional 1 hour. So this is the property that we're using, probability x greater than x plus t, given x greater than t. So if I know x is already greater than t, the probability that it's greater than an additional s amount above t is just, I ignore the t that I already know I waited for. I just look at the additional amount, the probability, the additional time I wait. Alright, so here if I already know the repair time exceeds 9, the probability that it exceeds, so it's 1 more than 9, it's just the additional amount. Alright, and this probability, again, I don't want to do calculus, so I can write it as, basically it's 1 minus probability x less than or equal to 1. To use a distribution function, you always want to write it in terms of probability x less than or equal to something. So that's just 1 minus f of 1. It's 1 minus f of 1 is 1 minus e to the negative lambda. That's negative 1/2 times 1. That's your answer. So for exponential distributions, this condition probability is very easy. It's just nothing but probability x greater than 1. If x had been uniformly distributed, you'd have to do some calculations. You'd have to use the formula for conditional distribution. So you'd have to write as probability x greater than 10 and x greater than 9, which is just x greater than 10 divided by probability x greater than 9. Problem 33. So in problem 33, we are again going to use this memoryless property of exponential distributions, and that's what makes this distribution so nice. It's like you don't need to I'll write down the problem. See how useful it is. Okay, so in problem 33, you buy a used radio. So Jones buys a used radio. So first of all, start by defining a random variable. So let x be the lifetime of the radio. In years. And we're given that it's exponentially distributed with rate lambda equals 1/8. So let me just write down the distribution function for this right away. It's 1 minus e to the negative 1/8. And the question is, what's the probability? So we know it's a used radio, right? So we know that the radio's been running for a while. But we don't exactly know how old it was when Jones bought it, right? 20x greater than 8. And we estimate the probability that it runs for 8 additional years after the 8 years. The nice thing about exponential distribution is, even though I don't know what A is, I can still calculate this probability, because this condition probability is just probability of the additional time. So, and this works only because it's exponentially distributed. So, and that's one of the reasons why we like to use this distribution, because for problems like this, supposing something's a used radio, you don't really need to know how old it is, okay, to see how much, what's the probability of it running for an additional amount of time. Because condition on how old it is, the additional amount of time, this probability stays the same, it's still exponentially distributed, because in terms of the additional amount of time. So this is just 1 minus probability x less than or equal to 8. And we use this only because it's exponentially distributed. And back here, so it's 1 minus f of 8. So it's 1 minus Okay, so someone come up to 25. So we have volunteers for 20, not 25, 24, right? 25 and 37. So volunteers for
How does that
25.
get to the negative 1?
Say that again, sir?
E to the negative 8 bits.
And then use the negative 8 over 8. I'm using, the parameter is 1 over 8, and my x value is 8.
Oh, okay. Yeah.
And then out of 39, so.
Yeah.
Can you erase this?
Yes.
Which problem is it you're doing? 25 on page.
How's it work?
226.
Alright, if we are interested in the absolute value of x being greater than 1/2, that means either x is greater than 1/2 or x is less than negative 1/2. Exactly. In problem 25, we're going to do a normal approximation to binomial, right? So x is the number of,
You do this either way.
Do you know which
You
number
do
he's doing?
make x either acceptable or
or,
unacceptable.
right, yeah, so choose which one you want to
I have
do.
a question.
Yeah.
For 25, you don't have to use a continually correct physics.
You do, when you do the normal approximation, you've got to do a continuous base. Yeah, correct.
So that's greater than or equal to, right?
1 minus a half.
Yeah, so what is the question?
What if you did it the other way? If you do it unacceptable, if you do it acceptable,
Wait, let me
if you do
say
it
that.
unacceptable, if we continue.
The most, so at most 10, so less than or equal to 10, right? So equal to 10 is also in there.
It's most if you
So, okay, the first thing is like frame the question. You have equal also here. If it was strictly less than 10, okay, you don't have to do continuity correction. But if it's less than or equal to 10, so you have to. You have to make sure that 10 gets included, so you correct it by 0.5.
You can also do it greater than one.
Yeah, but then, so then you say talking about number of acceptable items.
Yeah.
Yeah, the thing is, depending on how you framed your question, if you were doing something strictly greater than 10, then maybe then you don't have to do continuity correction. But if it's framed like this, less than equal to 10, you've got to do continuity correction. Okay.
I have a question for for this one. The condition NP equal minus P is equal to 7.125.
Okay, we'll take this condition to be as long as you get it to 5. I know on the review sheet I said 10, but in class I said 5.
5.
Yeah, so let's stick with 5. Because first of all, it asks you to approximate it, and n is pretty large, so yeah.
Okay.
so yeah, the first thing to do is identify what possible values it can take, and can multiply between 0 and 1. And so then we start with the distribution function, that the same time, so that's just x is between -1 and +y, and that is just this. Okay, so now we differentiate throughout, you get that equals this, and this the negative, so that's plus, that's right. Okay, so now it just, guess, yeah, no, this is right. So then what is fx of y is just going to be fx of y, it is, so y is some value between 0 and 1, so it's 1/2, right? And fx of negative y, since y is between 0 and 1, negative y between -1 is, so it's 1/2.
So it's one.
Yeah, it's 1.
That only makes it something.
Remember, these are only density functions, it's not a rate.
Very cool.
So basically, so what is this telling us? That absolute value of x is now uniformly distributed over 0, 1. Which makes sense, because if x is uniformly distributed between -1 to 1, the absolute value should be uniformly distributed between 0 and 1. Because it's a constant in the interval 0 to 1. Okay, maybe to be to explain completely, this one, if y is between 0 and 1, and 0 if otherwise. And we already know that because we know it only takes values between 0 and 1. So to be precise is this. So therefore, y, which is absolute value of x, is uniformly distributed. Yeah. This problem was 33, right?
37.
37, yeah. 37.
What kind of problem is this?
So is this an approximation? Or is that?
At this point, it is, it's equal,
It was
it's still equal.
So it was uniform.
Okay.
So it still has
Uniform
its x.
continuous?
Exactly.
Yeah, it was uniform. Yeah.
And then here is where it goes.
Exactly, because now this is not exactly normal, it's only approximately standard normal. So when you go from here to here, here we know that we're looking at x equals 0, 1, 2 up to 10. Here we're still looking at x equals 0, 1, 2 up to 10. That's right. 1.12, you can find that. 1.12, okay, fine.
Dr. Newman,
Yeah.
intuitively, you can kind of tell that y would already have also a uniform distribution. Because
Right.
every case you'd start off with, a uniform distribution and end up with something different.
This is just like
So a linear thing,
Normal approximation.
normal approximation to
let's see, what about if you take x squared? As like between 0 and 2. No, with x squared. So again,
What about those x cubed?
think anything
What
where
feels like x cubed?
x cubed, then should it still be uniform over -1 to 1?
Yeah. No.
With the cubed, so anything which is positive stays in the, let's see, left side there. I think that could also be uniform distributed, makes sense. Let's just see what we get. And then we can calculate that. Yeah, that could. Actually, even for x squared. Oh,
Plus or minus.
I think we did x squared in class, didn't we?
Mhm.
Yeah, so there you end up with a, you don't just get this, right? You get a
One-
1/2 squared
root
x.
Yeah.
So then it's not going to be uniform. Oh. Because with something like x squared and x cubed, the things, linear things, it's like with x squared, it's like seems like squish up some part and elongate some other part. So in that sense, you can see that the distribution doesn't quite stay the same. But with linear, yeah, it still sort of stays the same, right? So, yeah, so I think anything other than a linear thing or something like absolute value, I think everything else would be, would not be uniformly distributed.
That makes sense.
All right.
Was it,
Yeah.
can you explain the step going from where he finishes finding big F sub y and y to, when he goes up to little f sub y and y? I understand how he solved all that,
Okay.
and then going up to the,
Here.
yeah.
Okay. Now we just differentiate both sides. So we know that the distribution function of y is given in terms of the distribution function of x.
Mhm.
Okay. So now I'm differentiating both sides with respect to this little y.
Okay.
The derivative of this with respect to little y is just the density function of y at the point little y.